Hi everyone, and welcome back to part 4 of this video series on semiconductors. So in this video, we'll be talking about Fermi energy levels and also carrier concentration of a semiconductor in thermal equilibrium. So let's just start with the Fermi direct distribution function, which is basically this function shows a probability that a quantum state at energy E is occupied by an electron at some temperature of T. So what does this mean? So we know that a semiconductor has an energy band diagram like this. So there's a conduction band and a valence band. So there are many possible quantum states here of each of different energies. And so the Fermi direct distribution function basically shows what is the probability the probability that any of these states, let's say this point here, is occupied by an electron. And of course, this also depends on temperature. So this formula is Fe equals to 1 over 1 plus exponential of E, which is the energy you're trying to find, minus the EF over KT. So EF is the Fermi energy level. And the probability of the energy state of the Fermi energy level being occupied by an electron is always half. This is because when E equals to EF, like when you sub E equal to EF, Fe becomes 1 over 1 plus exponential of 0, which is just 1, so it's just half. Okay. So now let's look at the semiconductor at T equal to 0 Kelvin, so absolute 0. And actually at T equal to 0 Kelvin, Fe is equals to 1 for E is smaller than EF, and 0 for E is larger than EF. Why is that? Okay, so if you look at the graph, you can see it here. So this is where T equals to 0. But why is that? It's because you can see T is in the denominator of the equation. So for E equals to for E is smaller than EF, Fe will become 1 over 1 plus E of some negative number at the top over 0, which is just 1 over 1 plus E to the power of negative infinity. And of course, E to the power of negative infinity is 0, so this is equal to 1. And for E is larger than EF, the Fe is equals to 1 over 1 plus E, and this time is positive number over 0, so this is 0. So that's why at T equal to 0K, it is like straight down to 0, like it's absolute shift. But at T is larger than 0K, the electrons are able to gain thermal energy. So we have explained this in the previous parts, so you can go look at the other videos, like the earlier videos, to understand this. So electron gains thermal energy and can be excited to higher energy levels. So you can see the higher the temperature is, the less steep the gradient is. So the higher the temperature is, the less steep. So for example, the red color one is T2, where T2 is larger than T1. You can use this understanding method, or you can also just look at the equation. So, KT, and then, yeah. Of course, when T is larger than 0, the chance will no longer be so absolute compared to T equal to 0. So another property is that function is symmetrical. The Fermi direct distribution function is symmetrical about EF at all T. What do I mean by this is that the probability of the state with energy delta E above EF, which is just this, is equals to this. So it is equal to the probability of the state with energy E below EF being empty. So So the probability, okay, I'll just say that again. So the probability of the left side, which is the state with energy delta E above EF occupied by an electron, is equals to the probability of the state with energy delta E below EF being empty, so not occupied by an electron. So let's show this through this diagram over here. So here's EF, and I'm going to draw here EF. This is EF plus delta E. Of course, this is EF minus delta E. I'm going to draw this to the top. So this place here is this side, which is the 1 minus EF, 1 minus F of EF minus delta E. And so this gap is equal to this gap, which is F of EF plus delta E. So this function is symmetrical about all the temperature. So no matter what temperature, no matter what gradient you see on the graph, this will work. And let's just prove this mathematically. So we have F of EF plus delta E is equals to 1 over 1 plus exponential of delta E over KT, and 1 minus F of EF minus delta E is equals to, so this is equals to 1 plus exponential of negative E over KT over 1 plus exponential, then here's minus 1, and so this is actually also equals to 1 plus exponential of delta E over KT, and this is of course equals to this, so hence proven. So now let's try an example 4.1. Given that electrons in a semiconductor follow the Fermi direct distribution function, find a formula for the probability of finding a hole at energy state E. So let's try A first. So the probability of hole is just the probability of absence of electron. So actually it's the same as 1 minus the probability of an electron, which is actually 1 minus this from the formula above. And so this is just equals to 1 minus 1 plus exponential of E minus EF over KT. And then for the denominator, we are going to split it so that we can cancel some terms out. So I'm going to split this into this times 1 plus exponential of EF minus E over KT. So if you work this out, so cancel this to 1, cancel this 2, is actually the same as 1 over 1 plus exponential of EF minus E over KT. So if you look at these two formulas, so this one, which shows the probability of hole, and this one, which shows the probability of an electron, you can see they are actually very similar. The only part that's different is the E minus EF is switched to EF minus E. So it's very convenient to remember this in an exam, because many times they may ask you like, what's the probability of hole, or what's the probability of absence of electron. So instead of needing to derive it or doing 1 minus manually, you can just remember that it's switched around. So let's do part B now. So calculate temperature T at which probability the energy state 0.3 eV below Fermi energy 0.01. So we can just use the result from the previous part. And then we know that the exponential is this, we have to convert electron volt to SI unit because this equation is in SI unit. So the EV must be converted to joules. So this is 99. And of course, when you do some math and work this out, this is just 757 Kelvin. Okay, let's try another example, example 4.2. Consider two energy levels E1 and E2, with E1 is larger than E2 and an energy separation of 1.12 eV. So let's just draw this first. E1, E2. And the Fermi energy level EF is between the two levels, such that E1 minus EF is 0.3 eV. And so, of course, the distance between Fermi energy level and E2 is 0.82 because the total separation is 1.12 eV. So let's try part A. The probability that an energy state E1 is occupied by an electron is, this is just using the formula, so very straightforward. Again, you have to convert to joules because it's in SI unit. And the answer is 9.22 times 10 to the power of negative 6. Okay, part B is more interesting. The probability that the energy state E2 is empty. So this is just 1 minus F of E2. And remember just now we were talking about how the probability is symmetrical about the Fermi energy level, EF. So the probability that energy state E2 is empty is actually equals to the probability that an energy state 0.82 eV above the Fermi level, because okay, E2 is 0.82 eV below the Fermi level, so the probability that that is empty is equals to the probability that an energy level 0.82 EV above the Fermi energy level is filled by an electron. So again, you can just use the formula and the answer will be 1.73 times 10 to the power of negative 14. Okay, and let's try one last example before we go into carrier concentrations. So assume that T equal to 300 Kelvin, the probability that an energy state EY is empty is 0.97. What is the probability that an energy state 0.1 electron volt below EY is occupied by an electron? So again, 1 minus F EY, because it's the probability that is empty is 0.97. So let's use the formula we have obtained from example 4.1, which is this. Okay, so now we have EF minus EY is equals to KT ln 1 over 0.97. Okay, so I'm skipping a few steps here, but this is just math. So okay, so let's draw the energy band diagram. So here's EY, here's EF, and their separation is negative 0.090. So the fact that EF minus EY is negative means that EF is below EY. That's why it looks like this. And then now we have, what is the probability that energy state 0.1 eV below EY? So 0.1 eV below EY is here. So let's just call it energy state X. Okay. So this is 0.1 eV. So from this diagram, you can see that EX minus EF is equals to negative 0.01 eV. It's just 0.1 minus 0.09, so this is 0.01 eV. Okay, so the probability that this energy state EX is filled, again, just use the formula. Kelvin, and this is equal to 0.595. So that's the answer. So now we will move on to the density of states, which is basically the number of quantum states per unit volume, per unit energy available for electrons to occupy. So it is like the number of slots that each unit energy, like the number of slots for electrons that each energy state can occupy. It doesn't mean that the electron must occupy it, it's just the number of like slots that can be occupied at each energy level or each quantum state of the energy level. So the possible unit is just a number per cm cube per electron volt. So of course this is not the SI unit, but it's a commonly used unit. So the free electrons in 3D, for free electrons in 3D, the number of quantum states is equals to 4 pi times 2m to the power of 1.5, 3 over 2, divided by the Planck constant h cube and square root of that energy. So actually, I'll just draw this first, but later we'll see why we need it. So this is just energy. This is the density of states. So this is the conduction band and this is the valence band. So in the conduction band, the density of states E is equals to 4 pi. This is the effective mass of an electron over h cube, square root of E minus EC. So the distance between that energy and the conduction band. So again, if you look at the one of the past videos, we will know that at the bottom, near the bottom of the conduction band, we can have a parabolic approximation. So here, E minus EC is equals to the h bar squared, k squared, over 2 of the effective mass of an electron. So k is the wave vector, so it's basically like, so this graph is actually quite complicated in real life, but we are just taking the bottom and taking a parabolic approximation. Okay, so where does this equation come from is not part of this this video series. This requires quantum mechanics. If there's enough people asking, I'll make another video on that. But basically, in this module, you are given this equation. You don't have to derive it, so you can just take it as take this equation as what it is. So similarly for valence band, the density of the states in the valence band is 4 pi, but this time it's the effective mass of the whole because it's in the valence band. 3 over 2 over h cube times EV minus E. So EV is the top of the valence band. So again, there's a parabolic approximation that can be made near the top of the valence band. So here EV minus E is also similarly, it's just the same thing. Reduce Planck constant squared, k squared, divided by 2 effective mass of whole. So this will look like this. Okay, these two curves may not be like mirror images, because you can see it depends on the effective mass of the electron and hole, and the effective mass of electron and hole may not be the same. So it may not be mirror images, but how the curve exactly looks like is dependent on the effective mass of electron and hole. So we know that in the middle of EC and EV is a forbidden energy state. So the forbidden energy state cannot have any slots available for electrons to occupy. So in between EC and EV, the GE is equals to 0. So now let's move on to the thermal equilibrium carrier concentration. So for an N-type semiconductor, the majority carrier is the electron, and for a P-type, the majority carrier is a hole. That's why we look at the electron concentration and the hole concentration, respectively. So now let's first look at the N-type. So the electron concentration at energy E, which is this, electron concentration at energy E in the conduction band is the product of the density of states at E times the probability that the state is occupied by an electron. So it's just this, right? Does that make sense? So the electron concentration at energy E at a certain energy E in the conduction band is the density of states at E times the probability that the state is occupied by an electron. So this is just at a single energy. For all the energies, so we want to find the thermal equilibrium electron concentration fully in the conduction band. So we need to do an integration because we are trying to sum up all the individual electron concentration at each energy. So we'll take the integration from the bottom of the conduction band all the way to infinity of this. And we'll integrate with respect to E. So this is just equals to this, which is this. So this formula is actually given in your formula sheet. So most of the time you don't have to derive it like what we just did, but it is part of the module to need to derive it. So you are required to understand and write out this derivation. So NC is actually the effective density of states in conduction band. And what this is numerically equal to is 2 times 2 pi times the effective mass of an electron times kT over h squared, which is the Planck constant, to power of 3 over 2. Okay. And let's go to the p-type now. So similarly to the n-type, the whole concentration at energy E in the valence band is also the product of the density of states at that energy, and also the probability that the state is occupied by a hole, so or absence of electron. So this is just 1 minus Fe, because again the probability of hole is equal to the 1 minus probability of electron. So again this is at a single energy, so to find the thermal equilibrium hole concentration in the valence band, so we need to do an integration. So this time we'll integrate from negative infinity to the top of the valence band, or EV. So this is equals to this So again, it's around the same. And both of these formulas are given in your formula sheet. So, but again, you still have to know the derivation, although it's rarely tested. And so again, this is where NV is equals to 2 times 2 pi effective mass of hole times kT over h squared to power of 3 over 2. So you can see NC and NV is very, very similar. So again, this is effective density of states in the valence band. So as you can see, they are very similar. The only thing that's different is the effective mass of electron vs effective mass of hole. So this formula only applies for non-degenerate semiconductors, which means that EC minus EF, conduction band minus here. So you see the conduction band minus, okay, all these are possible Fermi levels. So the conduction band minus the Fermi level must be larger or equal to 3 kBt or 3 kT. The kB is just a Boltzmann constant, but I'm using K. And also the EF minus the EV must also be larger or equal to 3 kBt. So this is how it looks like. And because of this, we are approximating Fe, which is equals to 1 plus exponential of E minus EF over KT. And because EC minus EF is larger than 3 kT, for any energy above EC, so like any energy here, minus the EF must also be larger than 3 kT. So because it's larger than 3 kT, is much larger than KT. So we'll take E minus EF as like a very large, like much larger than KT. So the exponential term is very large. So we'll approximate this into minus E minus EF over KT. So if that was unclear, basically EC minus EF, the gap must be larger than 3KT. So that E minus EF will be very large. The exponential term is much larger than the 1, so we can approximate it into this. And this is required for this formula above to work. So it's the same for whole. So 1 minus so it's the same for whole. So 1 minus FE is equals to 1 minus this thing which is approximated into exponential of E minus EF over KT. Okay, so is the link of why is approximate is not as clear, but let us explain it. So because EF minus E is much larger than KT, so the exponential term here is actually much smaller than 1. So it's a very small number. So I'm just going to take this as, like, let's say x. I'm just going to take this as x. So 1 minus FE is equals to 1 minus 1 over 1 plus x. And this is equals to x over 1 plus x. So if you expand x over 1 plus x using the Taylor series, you can get this thing. So because x is very small, so if you use a small approximation, this is just equals to x. That's why 1 minus FE is just equals to x, which is just equals to this. So that's how we arrive at the approximation. Okay, so here's how it looks like graphically. So the GCE and GVE is what we have in the previous page, what we saw in the previous page, which is this. And then, of course, the FE, we have also explained why. This is obviously a semiconductor not at t equal to 0. That's why the FE is curved. And so the area here is equals to the P0, which is the whole concentration, and the area here is equals to N0, which is the electron concentration, because it's the sum of all the individual concentrations. That's why we have done an integration. Okay, so let's move on to intrinsic and doped carrier concentrations. So an intrinsic or undoped semiconductor has an equal number of electron and hole concentration. So it's just Ni equal to Pi. So this always holds for an intrinsic semiconductor is always the case. Using the equations we got earlier, we can get Ni is equals to Nc times exponential of negative Ec minus Ei over Kt, and Pi is equals to Nv exponential of negative Ei minus Ev over Kt. Hence, let's take Ni squared. Ni squared, again, because Ni equals to Pi, is equals to Ni times Pi. So Ni times Pi is equals to Nc and V. So we just multiply these two together. So Nc times Nv times exponential of, so two exponential multiplied together is just adding what's inside the exponential. So it's and this is equals to Nc and V of negative Ec minus Ev over Kt. And if you actually notice, this Ec minus Ev is also just the band gap energy. And if you notice even further, this thing is actually just equals to N0 equals to P0. When you have N0 times P0, you'll get the same result. Hence, the relationship is Ni squared equals to N0 P0. And this is extremely important. It's an extremely important equation that we will use a lot later. So this is valid for both intrinsic or extrinsic semiconductor. So Ni squared is equal to N0 P0. Always. Like when the semiconductor is in thermal equilibrium, is always true. Okay, so we have that. And now let's look at the doped carrier concentration in terms of the Ni, in terms of intrinsic carrier concentration. So N0 is equal to the concentration of the electron in the conduction band. So again, we have gotten this from the earlier part. And let's sub in, because now that we know that let's sub this in. So we know that Ni equal to Nc times exponential of that. So, and we'll sub that in. So we'll get Ni divided by exponential of negative Ec minus Ei over Kt, then multiplied by the exponential of this. So again, we have just add them together. So when you work this out, is equals to this. Okay, this formula is not in the formula sheet, but it is super useful. So you should definitely remember this. It's a super useful formula, so I'm just going to highlight it. It's a very, very important formula. This is also very important. So these two are very important. And so from this, you can also get, using some math, EF minus EI is equals to KT ln of N0 over Ni. So we have done the derivation for the for N-type. So let's do for P as well. So similarly, P0 is equals to Ni exponential Ei minus Ef over Kt. And of course, this also means Ei minus Ef is equals to Kt ln P0 over Ni. So also again, this is extremely important. You should definitely remember these two equations instead of having to derive it during the exam, because that will be wasting a lot of time. Okay, so now let's move to the intrinsic Fermi energy level. So remember that in an intrinsic semiconductor has equal electron and hole concentration, like we have explained earlier. So we'll equate Ni is equal to Pi, and we'll get Nc exponential of this is equals to Nv exponential of this. So again, we have got these two earlier on top. And we'll just do some math. I'm probably going to speed this part up. Okay, so now that we have this, we can rearrange Ei is equals to half times Ec plus Ev plus half Kt ln Nv over Nc. Okay, so here's what we have so far. And if you look at half Ec plus Ev, this is actually equals to the middle of the bands. So Ec, Ev. So when you add these two and divide by 2, you get the middle, exactly the middle. So this is E mid. You can either use this form, or you can sub in. Remember, we have Nv and Nc. We have found Nv and Nc earlier. So we can just sub this in. I'm just going to sub E mid because it's faster to write, but it's the same thing. Plus half Kt ln. So if we take what we sub earlier, we take what we found earlier. This is what it is. And also, so this is E mid plus, again, ln you can bring down the 3 over 2. So it's 3 over 4 kT ln MP over Mn. So again, this is the effective mass of the hole for MP and the effective mass of electron for the Mn. So you can either use this or this. You don't actually have to remember this because it's quite rarely tested, but it's good to know, and it's actually quite fast to derive as well, but you can just remember it so you don't have to derive it if you want. So the derivation is necessary for the example, so it's not a given equation, so it's not in the formula sheet, so you have to derive it. So example 4.4, find the displacement of the intrinsic Fermi level, EI to the center of band gap, E mid at t equal 300k, given that electron and hole effective mass is 1.1 m0 and 0.56 m0 respectively. Okay, so this is very straightforward. So we just sub in the equation, 3 over 4 kT ln and this is equals to negative 0.13 eV. Yep. So as you can see, 0.013 eV is a very, very small amount. So normally you can just in most questions 0.01 is a very small amount. So normally it can be approximated to E mid. So of course at 0, EI is exactly equals to E mid. But even for other temperatures like 300K, which is like room temperature, is negative 0.013 eV is still very small. So this depends, of course, this depends on the electron and hole effective mass. It also depends on the temperature. But normally, you can just approximate it to be E mid in most questions. So it depends on question. Okay, so now let's look at the thermal equilibrium majority and minority carrier concentration. So if you look at the third part of this video series, we will find that we know this too. But this time we know that N0 P0 equals to Ni squared, which we got from just now. So if we sub in the P0, so we know that P0 equals to Ni squared over N0, right? So if you sub in the P0 here, you can obtain N0 equals to Nd plus Ni squared over N0. So now this is a quadratic equation in N0. And of course, the answer can be obtained just through the quadratic formula. So that's how you find the majority carrier concentration and N-type. So of course, the majority carrier here is electron, and the majority carrier for P-type is hole. So it's the same thing for P-type. We just sub in the N0. And of course, you also get a quadratic equation in P. So why we only take the positive solution is because the negative solution has like no physical meaning. It doesn't make sense to take the negative solution, so it's quite meaningless. So we only take the positive solution. And so if you look at this, if you look at these equations, these two, we find out that if okay, let's look at the N-type first. So when the doping concentration Nd is much larger than the intrinsic concentration, like I believe for this module they use 10 times, but of course there's no fixed number, it's just approximation thing. So if Nd is much larger than Ni, then the 4Ni squared is actually very, very small in comparison to the Nd squared. So actually if it's above 10 times in this module, you can actually just assume it is roughly equals to Nd. So it's the same for the P-type. When the acceptor doping concentration is much larger than intrinsic carrier concentration, you can just approximate it into the acceptor concentration. Okay, so let's try an example. A semiconductor sample at T equal to 300K is doped with phosphorus atom. So I think this is silicon, but many things, yeah, I mean, can be many things. I mean, I know it's silicon because of the intrinsic carrier concentration is this, which is commonly accepted for silicon at 300 Kelvin. But anyways, a silicon sample at T equals to 300K is doped with P atoms to concentration of 10 to the power of 16 cm negative cube. So atom per cm cube. So there is 10 to the power of 16 phosphorus atom per cm cube. Given that intrinsic carrier concentration is 1.5 times 10 to the power of 10 per cm cube, calculate the thermal equilibrium minority carrier concentration. So to find the minority carrier concentration, we have to first find the majority carrier concentration. So, okay, you can see that 1016 is much larger than 1.5 times 10 to the power of 10. So we can just approximate. We can just approximate the majority carrier concentration to doping concentration, which is just 1016. So now to find the minority carrier concentration, which is the whole concentration, this is just this squared divided by 10 to the power 16. And this is equals to 22,500 atom per cm cube. So that's the thermal equilibrium minority carrier concentration. Okay, now the position of the Fermi level EF relative to intrinsic Fermi level EI and drawing an energy band diagram. Okay. So remember earlier we have found this equation. So from this equation, you can get EF minus EI is equals to KT ln of N0 over Ni. Correct? So now that we know this, we know that EF minus EI is equals to 1.38 times 10 to the power of negative 23 times 300 times ln of 10 to the 16, 1.5 times 10 to the power of 10. And so this is equals to 5.55 times 10 to the power of negative 20 joules, which is converting to electron volts, this. So now let's draw the energy band diagram. This is the conduction band, valence band. Again, see, for example, for this question, okay, for most questions, but for these questions as well, you can just let the EI be roughly equals to the emit. Okay, I wrote equals, but it should be the curly equal. So curly equal emit. And of course, the valence band is here, conduction band is here, and the Fermi level will be here. Write that more clearly. This is 0.347 eV. Okay, so yeah, that's the answer for this question. Example 4.6. A semiconductor sample is doped with donor atoms to a concentration of 2.0 times 10 to the power 14 per cm cube. At T equals to 310 Kelvin, the band gap energy is 0.9 electron volt, and intrinsic carrier concentration is 6 times 10 to the power 13 to power per cm cube. Find thermal equilibrium minority and majority carrier concentration. So okay, remember this time we cannot just approximate because it's not much more, it's less than 10 times more. So we have to find it through this method. So we have to manually calculate it. And so this is 2.17 times 10 to the power 14 per cm cube. And now that we know the majority carrier concentration, which is electron, we can find the minority carrier concentration, which is whole, by dividing Ni squared over the majority. And this will be 1.66 times 10 to the power of 13 per cm cube. Okay, so now let's move on to part B, the position of Fermi level relative to intrinsic Fermi level. So again, we'll just use the same equation as the previous example. But this time the temperature is at 310 Kelvin. So we just find this. And this is just equals to 5.50 times 10 to the power of negative 21 joule, which is 0.034 electron volts. So now let's draw the energy band diagram. So again, you can approximate EI to be emit. And of course, EF is here. So by now you should have noticed that for an N-type semiconductor, the EF lies slightly on top of the emit or the intrinsic, and for P-type it lies under the EI or emit. Alright, so now let's move on to our last part, which is compensated semiconductor. So a compensated semiconductor is just a semiconductor that's not doped with like either donor or acceptor, but it's doped with both of them. So this can occur during the fabrication of the semiconductor, and it sounds a bit more complicated than it actually is. So but basically when the donor impurity, when it's doped with more donor impurity, it becomes N-type. When it's doped with more acceptor impurity, it's P-type. And of course, if it's doped with the same amount, then it's just intrinsic. So it depends on how much is doped on each side, and depending on which is more, is either N-type or P-type. So it's basically the same as a single one, it's just doped with both, and it's like the net amount instead of just one. So at sufficient T in where the extrinsic region where all the impurities are ionized. So for what this sentence means, you can look at the third video. So essentially it just means where in the temperature range that the semiconductor achieves its desired properties, we have P0 plus ND is equals to N0 plus NA. So it's just the same thing. So for this example, I'm just going to consider a P-type, an N-type first. So again, we have a quadratic equation in terms of N0. So the solution for this quadratic equation is very straightforward. It's just this. So as you can see, it's basically the same thing as just now, but instead of just using like the donor or just using the acceptor, we are using the net doping. So it's the same for the P-type. So instead, because there's more acceptor than donor in P-type, is Na minus Nd instead of Nd minus Na. Yeah, so it's just that. And we are at our last example. A germanium sample is doped with donor impurities to a concentration of Nd equals to 5.8 times 10 to the power 14, and acceptor impurity to a concentration of Na equals to 5.4 times 10 to the power 14 per cm cube. Given that the intrinsic carrier concentration at T equal to 300 K is 2.4 times 10 to the power 13, calculate the thermal equilibrium majority and minority carrier concentration. So for this question, because Nd is larger than Na, so it is N-type, right? So N-type means the majority carrier concentration is an electron. So N0 equals to, we are just going to use this equation. So it's just 0.4 10 to the power of 14 plus root of 5. Okay, I'll just take 0.4 immediately again. Over 2. And what is this? This is just 5.12 times 10 to the power of 13 per cm cube. And again, the P0 is just, I'm running out of space, but it's okay. P0 is just Ni squared over N0. So this is just equals to 2.4 times 10 to the power of 13 squared over the 5.12. And this is 1.12 times 10 to the power of 13. So yeah, that's the equilibrium hole and electron concentrations. And yeah, that's the end of this part 4 of semiconductor physics, this video series. If you enjoyed it, please give it a like and check out the other videos in this video series. Yep. Have a nice day.